Today's video might be a bit longer. I might even have to split it in half. But I'm going to try to show you how to derive the best fit least squares line. This is tough, this is hard, and so I'm going to show you the long way. In the next video, we're going to come back and I'm going to show you sort of like an easier way and how I would do standard curves. But this shows you everything that's in there, so this should be a nice way. If you can do this, you can do anything. So I'm going to hand out this phosphate lab, and if you scroll near the back of it, you'll see this is part 2 for the homework. And what we're trying to do is when you have a standard curve, so if you have phosphate concentration on the x-axis, absorbance on the y, you're going to want to get your standard curve for the best fit line. So we're going to actually do this whole best fit line ourselves and calculate everything. It is thick in the weeds of math, but if you can do this, you can probably do almost anything in Excel. And I have it set up for you. So here, if I jump to Excel, what I have here is I have it so it's like this is the Excel sheet. We have the equations we have to use, right? And then for each value, we have hints, right? And so we have all these hints. So if you go through and fill them out, you'll be able to do it all, right? And so here what we have, this is what, imagine we were in the lab. We made standards for phosphate, and we measured the absorbance. And now we want to go figure out our unknowns. So the first thing I always do whenever I make a standard curve phosphate and absorbance, I always just make a graph of it. So I'd highlight these. I'm going to cheat here. So I'd highlight them, right? I'd go to insert chart, right? And I'd insert a scatter. But now let's see, boom, we have it. But that's not how we do it. So that's not what we make. So you can actually make one that looks nicer. Here is mine. So I made a nice standard curve, phosphate concentration. Here's our absorbance. Here's our best fit curve. Here's our best fit line. But we're going to try to do this all by hand now, right? So we're going to try to go through all this and do it by hand. So you move our graph over. So I expect you all to be able to make this nice graph yourself. You know how to do this. Oh, I went too far over. You know how to make a really good looking graph, so you will be able to do it. So now let's go start working on our Excel sheet, right? So here's our phosphates, here's the absorbance, and here's our equations. So we're going to work down and see if we can get these equations to fill in over here. So first thing as I said, each of these I have little hints for what you need to put in there. So n, whenever you see n, that's the number of samples you ran, right? So it's going to be 1, 2, 3, 4, 5. So we have 6 of those. I'm gonna hardwire in there, but you could also use a count. So you could do a count, and you could count how many you have up there. 6. X bar, right? And then here's the equation over here. X bar, if we go through here, that's the sum of your xi values divided by the number of standards you ran. So we're actually just getting the average. So x bar, whenever you see a bar, it's the average. So if you do the sum divided by the n. So I'm going to actually do the sum of our x's. These are our xi's, right? So it's individual ones. That's why we have the x of I. So there's the sum, right? So now we could do the average, or we could just do the sum divided by the count, right? And we get 2.9. Then we want the same for y bar. So we're going to drag over our sum, right? And then we'll do y bar, so it's equal to sum divided by count, right? And we get our 0.0067. So we have those. And now we want m, right? And what is m? We'll look at our hint. M is the number of replicate analyses you ran for your standard curve. So we only ran our standard curve once. That's a 1. And then degrees of freedom, we'll need this later. This is, I always have trouble with degrees of freedom. So we start with 6, because that's how many standards we run. Then we lose degrees of freedom for the intercept and the slope calculations, right? So it's going to be equal to n minus 2. Okay, so we're getting there. We're making progress. Now here comes the real ones, a squared. So if we look over here, we have a squared. There's 2 forms of it. They both work. I'm going to do this right form, which is the sum of xi squared. So we don't have that yet. So here's our xi squared. So we need to make this. This is xi squared, right? So we can then drag those down. We have those. So it's going to be the sum of xi squared. So we need the sum. I drag our sum equation across. We're good. Right, well, we lost our border down. Let me add the border back in so it looks nice. Right, so now we have our sum of xi squared. Do we want the sum of xi squared over n? So it's actually the, right, that's slightly different because the sum of xi squared. So let's see if we can do this. It's going to be equals to the sum of xi squared, so that's this, minus the sum of xi squared divided by n. Right, and so there we're good there. Now we want our b squared. So if we look at this as the sum of yi squared, so we don't have those yet. So we're gonna make those. We're gonna square our yi's, drag them down, messed up our border, put our border in. Right, we're gonna make this sum. Over here we add the sum. Right, and so now we can do our b squareds. So this is gonna now equal to the sum of yi squared minus the sum of yi, the whole thing squared, divided by n. And you can see those are, right, there's two slightly different numbers. Now we get our b squared. And now we want ab. And this is not a times b. There's rounding errors, other issues that cause it. So we look at our question, we want our equations, we look at the sum of xi yi minus the sum of xi times yi over n. So we need our xi yi, so this is xi times yi. We're going to drag that down, fix our border, and we're going to want the sum. So we drag over our sum, and we have it. So let's see if we can do this. So it's going to be equal to the sum of xi yi minus the sum of xi times the sum of yi divided by n. And we don't need parentheses because it's all, divided by n, sorry about that. And we don't need the parentheses because it's all just multiplication and division there, so it should work. So we are good. So breathe. Now we'll breathe because we're moving along. We're doing nicely. And now we're going to want to calculate. This is where we actually calculate our slope. This is where it's what we actually want. So if we do, our slope is equal to ab over a squared. So we have those. So it's ab divided by a squared. And it's 0.026483. Then we want our intercept a, which is equal to y bar, our average, y bar minus b, b, our slope, times x bar, right? We're just getting, and that's 0.00424. Let's see if that actually matches what was on our, now this is where it hurts that I lost my, there we go. Let's see if it matches what's on our graph, right? Did we calculate the same as Excel? Slope 0.0265, boom, yep. If we round it, it'll be the same. So, right, and then intercept 0.0004, right, 24. It's rounded, it is the same. So we match exactly what Excel is. Oh, I did it again. It's calculating. So we're going to leave our graph here in case we need it again. So we're doing great. Now this is where things get a little bit tricky because now we want to start thinking about errors on things. So these equations get even harder, right? And so this is going to be SR, the standard deviation for the residuals. So if you look at our SR equation, that is a biggie. That's a biggie. So we're going to need to work on this. So we're going to go. So I'm going to breathe deeply. And you all could do this. You do the square root. Right, I'm going to put both parentheses there. Then I'm going to go in there and add a couple spaces. Right, so then we're going to need another one because we want the top. So I'm going to open another equation, right? And so we're going to have b squared minus little b squared times a squared. I'm going to close that because that's the top. I'm going to divide that whole thing by n minus 2. N minus 2. We should close that, and I get, right, we get 0.002571. And the interesting thing is there's a function in Excel that does this, sty x. So if we do that, we can do up known y's, comma, known x's, close. We get the same number. So we're in good shape there. And then if you ever want to, now when you want to get the detection limit on our, whenever we want to calculate the detection limits, what you do here is you now, to calculate the detection limits, I don't have it here, I'll put in a note, it's always equal to 3.3 times sty x, or the standard residuals, divided by the slope. And this will then give you the detection limit of your sample. So the detection limit we get, there's two ways to do detection limits. This is one way, it's 0.32. So that's the lowest concentration we'll be able to detect. Then we'll calculate the standard deviation for the slope, SB. So if we look over here for SB, it's SR over A, or the square root of SR over A. So we're gonna do this. That's right. So we're gonna do this. We're gonna do equal to SR divided by the square root of A squared. We get 0.00307. So we are in. We keep moving, and now we're going to do SA, which is a standard deviation for the intercept. Okay, so for this one, so SA, we're going to look over here. Right, it's SB times the square root of the sum of xi squared over n. I'm breathing deeply. These equations get tough after a while. So I'm going to do equal SB times square root sum of xi squared. We're going to go over here, xi sum divided by n. We get 0.00137. We're in great shape. But sometimes there's two ways we do the detection limit. You can use SA also. So it's equal to 3.3 times SA divided by slope. And you can see that one gives you a little bit lower detection limit, but we're going to go into the details next week on. They're slightly different, but we can use either. Okay, now we want to calculate our R squared. That's sort of what we've been waiting for, right? To get this R squared. So everyone likes to see their R squared. So let's see if we can do this. So if we look at our equations over here, it's AB squared divided by A squared B squared. So if we go AB squared divided by A squared times B squared. Since they're both on the bottom, I did parentheses. Ooh, look at that, 0.9994. We go up to our thing, 99. Oh, we got it rounded off slightly different, but we got the same answer. All right, so we are great. And then the F statistic is sort of looking for significance. This the F statistic tells us how significant. It's going to help us determine significance. I don't use it that much, but it helps you sort of calculate a p-value. Right, and we're not going to need this, but we're going to put it in for thoroughness. Oh, so we need YFit minus Y bar squared and YFit minus YI squared. So we need two new parameters up here, right? So we need YFit. Oh, we don't have YFit. So YFit is once you've calculated B and A, you can calculate the predicted phosphate. It's like what you should have gotten based on this standard curve, right? So it's A plus B times XI. So it's equal to A plus B times XI. But this is going to fail when I drag it down, so I'm going to put in dollars. I'm just going to put both because we don't need both, but I'm going to do it because I'm lazy, right? And then this should be our Y fits. Cool. And so now we can do Y fit minus Y bar, right? That's the average. So we do, let's see if we have this. We can do equal to parentheses, YFit minus Y bar. Let's go get our Y bar over here. We're going to want to hold that one constant, so dollar signs, parentheses, squared. Oh, I did that, and then we should be able to drag it down. And we're going to need the sum, so I'm going to drag these across. Now we need YFit minus YI squared, so it's equal to YFit minus YI squared. Then we're going to drag this down. We're going to want the sum. Let's fix our borders. Right, and you're going to say, oh, those are zeros. Something's wrong. But it's just because they're small numbers. If I click on these, I click up here, I'm going to add some more decimals. And there you go. There you can see them. They are looking good. Now we can go calculate our Fisher F statistic. Right? So it's equal to degrees of freedom times the sum of Y fit minus Y bar. Okay, see if we can remember that. So it's equal to degrees of freedom times Y fit minus Y bar squared, that sum, divided by this. And we get a monster value, 7,000. So this is, I set up this little table for us here showing the critical values. So you can see if you want to be at significant at the 0.1 p-value, you have to be greater than 4.54. We're so there. So look, at the 0.01 value, to be greater than 21, we're at 7,000. So we're really significant. So we can say less than 0.01, but you usually don't do that with standard curves. Okay, then the last thing we want to do. Now imagine you made this standard curve. We have this beautiful standard curve, right? We have our graph, but we want to calculate an unknown. So we have sample 1. We went and measured its absorbance of 0.09. What's its value of phosphate? So 0.09, if you look up here, it's going to be somewhere in this 0.09, somewhere in here, between 0.053 and 0.12. So it should be this 2 to 3 range. But we want to calculate it for real, right? And so the first thing you want to do is this is the absorbance you measure. And this is going to go by different names, YC or Y or YC bar or YI, depending where you look on the equations. The first thing you do is you want to calculate the concentration. And this is just simple. You know, Y equals mx plus b. And so you just solve for x. X equals y minus a over b. So you go equals y minus a divided by b. And you have it, 3.38, just exactly what we said. Now let's put our dollar signs in. So we're going to want to put dollar signs here. And so you can imagine, look, we have these 6 samples. Let's figure them all out. So 0.2, so 0.2, that'll be 7.54. 0.008, oh, that's low. 0.29. 4A, that's sample 4, 0.11, 4. Right, then we have these 3 triplicates. So that's fantastic. We have our absorbance, we calculate our concentration. Now we want to figure out the error. There's 2 types of errors. This SC error is just based on the standard curve. And this is the most brutal equation yet we have here. But we can estimate an error based on how good our standard curve is. So let's see if we can get that in. Breathe deeply, get ready, equals SR over B. We need dollar signs. We want SR divided by B. I'm going to put all dollar signs. We want to hold those constant. Right? Then we're going to scroll down. I'm going to hold that whole thing times the square root of 1 over m. If you remember, we have m up here, so 1 over, nope. But this m is, oh, this m is funny. Right, this is the funny m, which I always get wrong. Right, and this is the m for the number of replicates. And I have it here, don't mix up m's. This is 1 over number of replicates here. So this one plus 1 over n, which is our n above. Okay, oh, we don't want dollar signs here because we're going to want this one to move with us. That was almost a big mistake. So I keep them. So now 1 over n, so we go up here for our n. So how well we did with our standard curve. All right, so we scroll back down. Then I put a plus, put a space. This is the hard part. YC bar, I have my little note over here, YC bar minus Y bar up here. We need dollar signs on that. Get our parentheses right. We want that whole thing squared. Then we want to divide that by b squared. Oh, we're going to divide by two things. We need parentheses. B squared times a squared. Close that. Close our square root. Hit return. Oh, I have an error. Oh, look, I keep on hitting those periods in there. There we go. Oh. I'm going to I'll say yes on the correction. I don't know what it's doing. Oh, and that actually worked. So if we look, our parentheses are lined up. We are good. Okay. And so now what's it saying? What this just did, this SC error, this is saying based on doing one replicate and their standard curve, this is what our estimated error was. We can now, if this works, we'll drag it down. Oh, and something went wrong. So did something wrong. So, right, we forgot this B24 have dollar signs. And now I'm going to try dragging down again. Let's see. Still wrong. So this is, oh, and we also need this B20 to have dollar signs. Let's try again. There we go. So now you can see these are the estimated errors. So 3.38 plus or minus 0.11 based on the standard curve. And if you look for this third sample, we did 3 replicates, right? But the concentration went down, so the error went up. So that's a little bit crazy. But let's see if I'm going to put in, hang on a sec. If we had a higher absorbance, something is wrong. Because you have number of replicates, it should go down. So I have something wrong in my error calculation. Let's see what it is. Oh, I think I see it. I think I see it. Look, I forgot dollar signs here. You all should have said something if you saw it coming. All right, I was wondering. Oh, there it is. See, as your number of replicates goes up, your error goes down. That makes sense. And so now we can put the errors here. But here, for these next 3, I'm going to show you 2 more tricks. So this was the same sample we ran 3 times. And what you did, since you ran it 3 times, you actually have a better estimate of error. You can just take this average of the 3, which is what you would do. You take the average of these, of the answer. You would get 4.77. And then I would just take the standard dev of the concentration, 0.58. So you can see this standard deviation does not match your estimated error on the standard curve. I like these better usually because this is where you actually ran 3 samples together. So look, you have 3 samples, 4A, 4B, 4C. So this is telling you your true errors that takes into account everything, collecting the samples, running them, etc. So that's a much more comprehensive way of doing error. And then there's finally one last thing we're going to check and we'll get into. Remember we determined detection limit up here. We're going to say our detection limit was 0.32. So if you look here on this sample 3, it was less than 0.32. So this sample, that's our concentration, but it's actually going to be non-detect when we're done because it's below what we could detect. So we don't know if it's that because it's below what our standard curve could detect. Anyway, that was a ton. But if you look at it, we're going to go back and do this a much easier way. But if you look, we have this amazing standard curve. You can calculate your concentrations. And this is sort of the hardest Excel we did. Look at these equations we added. And if you can do this, you can probably add almost any equation to Excel. Good luck.